Hey guys, I forgot I was on. How's it going? Hey guys, what's going on? I'm gonna wait a few minutes until a few people come. Hope everybody's going okay. Hope everything's going okay. What's up, guys? Gonna get this started real soon. We're gonna be talking about the basal ganglia again. Our last discussion was on the basal ganglia. We went over the structure and the function, and remember Muhammad Ali. Um, you know, um, uh, the 24,000 blows to the head. It's too much. I think his um, basal ganglia became swollen with the inflammation, that chronic inflammation. Eventually resulted in there was nerve fibers dying, and accumulated death meant that there were a lack of dopaminergic neurons in his basal ganglia. And overall, because there are deficit, fewer neurons, there were fewer neurons producing dopamine. And because you have fewer neurons producing dopamine, the entire network is hypodopaminergic. And that's one of the reasons why everything is immobile. That's the reason why the facial expression is sort of mobile, the stupor, slow movement, and things like that. That signaling really isn't working because there's not enough dopamine to power the networks, right? And we started using the strategy of carbidopa levodopa, which is increasing the amount of dopamine available and try to increase the production of dopamine by the nerve cells that are left. And hopefully those nerve cells can increase the dopaminergic output enough to make that tract less hypoactive. At least you want it active enough so the person can have a reasonable life so they don't have to be dependent upon someone else. So that was basically the pathology and the basal ganglia. Remember, in Parkinson's dementia, it's the buildup of those intra-inclusion bodies. And again, that debris, that intracellular debris can get so large that we read that it can actually displace the nucleus. I didn't think it got that large. But yeah, that may be the source of why, that may be the mechanism. And so in Parkinson's, you confirm it upon autopsy. So remember, that's the structure and the function of the basal ganglia. And today's discussion is going to be about the networks within the basal ganglia, right? Because we know that the basal ganglia is responsible for movements. And so we know that Parkinson's dementia is strictly the damage to certain nerve fibers in the basal ganglia and the mechanism is via the intra-inclusion bodies. In Huntington's disease is actually a genetically autosomal dominant disease process that also is a change in the base pairing that causes malfunction in one of the networks inside of the basal ganglia. So we're going to look at the basal ganglia, look at the networks, and look at the receptors on the network. And after we understand the receptors on the network, then we know how to use our medications, right? So let me see here. So let's see. Okay, here. All right, basal ganglia. Let me just go through this real quick. The basal ganglia are a group of subcortical nuclei found in the brains of vertebrae. All right. And so here's sort of like so it's a cluster of different nuclei, right? So here's the whole cluster that makes up the basal ganglia. Here's an interior view this way. Okay. The main functional components. Okay, striatum. Okay. the ventral striatum, and the globus pallidus. Oh, globus pallidus and the ventral pallidum. Okay, the substantia nigra and the subthalamic nuclei. Okay. Every time I read up on this stuff, I feel the same way. I feel like I get confused even more. It's been like 25 years. All right. Okay. So that's the basal ganglia. And so disorders of the networking in the basal ganglia can produce movement disorders. The movement disorders are so sometimes called Parkinsonism. Parkinsonism. Let's see here. Okay, I think I'm good with that. Okay, here, next. So here, went ahead and did a AI search here. Show me the pathways and the receptor profiles for the basal ganglia. So basically, we have an idea of the networks in there and how they operate, and the receptors, and we sort of know what to choose. Basal ganglia pathways and receptor profiles. Okay, the basal ganglia, a set of subcortical nuclei, which we understood that, play a critical role in controlling movement. Hey, listen, learning, cognition, and emotion. Let's focus on movement for now. That's the simpler one of all these options. They're involved in two main pathways that exert opposite effects on movement: the direct pathway that facilitates movement and the indirect pathway that inhibits movement. Now, the design of the basal ganglia, this architecture, the direct pathway, the indirect pathway, things like that architecture has been preserved throughout all of the mammalian species, it's not just in humans. And so, it's important to sort of understand how important this network is, and how fundamental it is as having a mammalian experience. You have all of these capabilities because of the way this network is sort of designed. It's very interesting. So here, direct pathway initiates voluntary movement, right? Indirect pathway inhibits or suppresses unwanted movement. Here, this hyperdirect pathway provides rapid, broad inhibition of motor output, particularly for suppressing impulsive actions. Okay. And of course, it's primarily modulated by dopamine. And then you have some other neurotransmitters that may be located in other parts of the basal ganglia. Like this isn't one part of the basal ganglia, this is the other part. These are the different parts. So here in a striatum, GABAergic neurons, GABA, yep. Basal ganglia produces excitatory. So this subthalamic nuclei, GABA, glutamate right there, GABA. And so, these are glutamate, highly glutamate increase, excitatory, GABA inhibitory. It's interesting that the predominant neurotransmitters at this location here, both, remember, in the other, the mesocortical pathway, the mesolimbic pathway, these other pathways, it seems like the dopamine was the most prominent neurotransmitter, but then they put an emphasis on GABA and glutamate on these two, excitatory and inhibitory. I guess those are the only thing you need to know in muscle movements. Okay, here. All right, so the direct pathway facilitates voluntary movement. Okay, cerebral cortex sends excitatory glutamatergic projections to the striatum. Okay, great. So, okay, cerebral cortex sends excitatory glutamated projections to the striatum. The indirect pathway, the striatum sends inhibitory GABA to the external globus pallidus. And so this is actually, the actual step-by-step mechanism. Very interesting. Okay, so let me see here. The hyperdirect pathway, provides rapid, broad inhibition of motor output. When you got to stop suddenly, I guess. pathway is monosynaptic, excitatory glutamatergic projections directly from the frontal cortex. That's the frontal lobe. That's the seat of your executive functioning. That's all decision making. So you mean to tell me this hyperdirect pathway is the monosynaptic straight from the frontal lobe? You see, the frontal lobe is what your seat of your executive functioning, and that's the location, that's the final stop to suppress or shut things down. And it's interesting to see that it's connected, the frontal lobe is connected through to this basal ganglia via by a monosynaptic. So one synapse. It must be very important to give the frontal lobe direct contact to the basal ganglia to shut everything down. Amazing. Okay, dopaminergic modulation. That's the standard nigra. Okay. It always gets like this for me. Anyway, dopamine has a dual effects, and it excites the direct pathway via the D1 receptors and inhibits the indirect pathway to the VT2 receptors. Oh man. This delicate balance between the pathway is essential for proper motor control. I didn't know that was the toggling mechanism right there. Okay, dopamine has this dual effect. It excites the direct pathway via D1 receptors and inhibits the indirect pathway via D2 receptors. Oh, okay. Okay, other neurotransmitters and receptor distribution in the striatum, mainly composed of GABA. Okay. Look, globus pallidus contains primarily GABA. Right, substantial nucleate glutamate. So remember, GABA is we have to go through GABA. It's another one of these huge G proteins that are very important. And GABA is I think it's the A site of GABA. Check this out, A site of GABA that targets the benzodiazepines. And so you can see with patients with extreme psychomotor agitation, combativeness, and aggressiveness, now you can see how given that IM Ativan or Valium or benzodiazepine can help with the psychomotor agitation, combativeness, and aggressiveness right away. And we use those in an urgent situation to sort of help deal with the agitation. And so now you can see exactly what the receptors on there. I think you're going to be experts at treating this thing. I think you do very well. Okay, let's look at the here list of pharmacological treatments for disorders involving the basal ganglia. So what are the treatments for the different disorders involving the basal ganglia? Remember, we went through Parkinson, right? We went through Parkinson's disease, right? Okay. All right. Okay, levodopa, often combined with carbidopa, is the most effective medication for managing Parkinson's symptoms by increasing dopamine levels in the brain. It should say more specifically to increase it more in that it does increase it throughout the entire brain, though. But okay, dopamine agonists. Okay, mimic dopamine's effect in the brain and have a longer lasting effect than levodopa. See, I'm not really familiar with, and the type of work I do, I'm not really familiar with using the dopamine agonist as much. I think that's an area that I need to sort of look into, because in many of these cases, when you see them in this hypoactive state, the psychomotor slowing, psychomotor retardation, you sort of look at them as being hypodopaminergic, and to be able to use the dopamine agonist to increase dopamine throughout the brain would be really an interesting strategy. I gotta take a look at that. If anyone know anything about that, just send me a link or something. Okay, MAOB inhibitors block the breakdown of dopamine in the brain. Okay, making more dopamine available. Yep. Okay, COMT inhibitors. Okay, helps levodopa therapy last longer by blocking enzymes that breaks down dopamine. Yep. Block the breakdown of dopamine in the synaptic cleft. Anticholinergics restore the balance between dopamine and acetylcholine, easing tremors and muscle stiffness. Benzotropine. Oh, how you know Cogenta restores the balance between dopamine and acetylcholine? Very interesting. Amantadine may help people with mild Parkinson's disease by increasing dopamine availability. Okay. So these are for Parkinson's disease, which is basically deficits of dopamine. Dystonias, another type of movement disorders. Okay. Huntington disease. Okay, let me just go through. They don't have the mechanism here. Either autosomal dominant transmission, and they're here are the medications for that. Tourette's syndrome. Okay, medications blocking or lessening dopamine. Antipsychotics like fluphenazine, Haldol, Risperdal, I've never seen that, are effective in controlling tics. However, they may cause side effects like weight gain and movement problems. Okay, so we use those in Tourette's. Botulinum toxins can help simple vocal tics. Okay. Okay, I don't know about those. Okay, important selections. Okay. All right. So we're at the 16-minute point. I only wanted to have these run for around 20 minutes, and I figure it's probably unless I have your attention for. And so let me see if you guys have any questions about the basal ganglia, and then I think I'll end this series on the basal ganglia. Let me see. I think this is like my third one. I don't think there's nothing else to talk about. Let me see. Okay, basal ganglia key networks and pathways. Okay, basal ganglia breakdown with Muhammad Ali. Okay, yeah, I think this is it. Yeah, I think this is it. Okay, so let me see if we have any questions. Okay, so I say, hello, Doc. Hey, what's going on, buddy? Good to see you, Doc. Good to see you, buddy. Okay, okay. Hey, Doc, good to see you. Hey, buddy. Okay, let's see here. Direct and indirect pathway. How does it differ? Let me just go through here real quick. Direct pathway initiates voluntary movement. Indirect pathway inhibits unwanted movements. The hyperdirect pathway shuts everything down. Got it? Okay, next is, okay, how does dopamine influence basal ganglia function? It helps out a lot. Hypodopaminergic states means the networks that are highly dopaminergic seem to be hypoactive. So in this basal ganglia, the dopamine is one of the major neurotransmitters that's used in transmitting the signals. If the dopamine levels are not being produced because the genetic programming is such that it's not being produced, or you don't have enough supplies, like starvation or something like that, infections and things like that, illnesses, or the tissue is being destroyed through inflammation or damage or something like that, then you're not producing enough dopamine, and so the whole network is hypoactive. Hey, Muhammad, what's going on, buddy? Doing fine, buddy. Nice to see you. Okay, let's see here. Can brain training or lifestyle changes improve basal ganglia health? I think I think using your basal ganglia, like a lot of exercise, a lot of activity, I think it definitely feeds back on the whole system. For example, let's say it's a beautiful day today. Let's say you're walking for an hour, one way or the other, along the lakefront, using your basal ganglia, right? But the experience is going to be so rewarding. You're going to have that environment is going to have a significant influence on you. I think the influence, the whole cycle of using your basal ganglia, getting out there, experiencing the environment in a positive way is all the things that can help improve your life and decrease your suffering. Okay, let's see, next question. What's the link between the basal ganglia and habit formation? It's like, I think it's more like the learning portion of it is more like conditional formatting. No, not conditional formatting, conditional learning. And I'm not sure if I'm correct on this, and I believe that does take place in the basal ganglia. And so with conditional, let's say with people who use substances, they may get spontaneous increases in dopamine simply by returning to the places that they used or the people that they were around. And the reason why is their body is reacting to the previous times that they were there in the environment. They went there in the environment around the same people. They got an increased level of dopamine, and automatically they start feeling better. I think that's that's the conditional formatting process that happens in substance abuse. And so that's a very tricky process because their brain makes them feel the most comfortable and at ease at the the very place and around the very people that they're most at risk at, So that's another issue. Okay, so here we're at the 21 minute mark. Is there any other questions, guys? Okay, so if you don't have any other questions, then I'll see you guys later. It's been a pleasure, and I'll talk to you guys tomorrow. Thank you so much. Read out. Basal ganglia.